Have you ever just stopped and wondered what's really running the show inside your body? It's not some kind of magic, it's chemistry. Pure, high-speed chemistry. And the master conductors of that whole orchestra? Well, they're called enzymes, the invisible engines that make life as we know it possible.
Okay, let's just jump right in with a question that sounds, well, kinda impossible. Your body is a chemical factory, right? It's running trillions of reactions every single second. But here's the crazy part. It does all of this at a nice, comfortable 37 degrees Celsius. If you tried to do that in a chemistry lab, you'd need some serious heat, maybe some extreme pressure. So, what's our secret?
And that question, that incredible puzzle, brings us right to our first big idea. The seemingly impossible speed limit that life has to work with, and the huge problem that this creates.
I mean, think about it. The conditions inside our cells are, frankly, terrible for most chemical reactions. They're mild, they're gentle, they're stable. Without some kind of secret weapon, the reactions you need to digest your lunch, build muscle, or even just think a thought would take, well, maybe years, if they even happened at all.
So, how does life get around this massive problem? It uses nature's ultimate solution, enzymes. These are the biological catalysts that make the impossible possible. They're the heroes of our story.
All right, let's get a really clear definition down. An enzyme is a catalyst. That just means it dramatically speeds up a reaction. It's almost always a protein, and this part is absolutely crucial. It isn't used up in the process. A single enzyme molecule can do its job over and over and over again.
And when I say speeds up, that is a massive understatement. We are talking about mind-boggling acceleration. Enzymes can make reactions run up to 100 million times faster. To put that in perspective, that's the difference between something taking 1 second versus taking over 3 years. It's a total game changer.
So how in the world do they actually do it? How do these tiny little protein machines pull off these incredible chemical feats? Let's pop the hood and see how they get to work.
Every chemical reaction has to overcome an energy barrier. It's called the activation energy. The best way to think about it is like trying to push a giant boulder over a really tall mountain. Without any help, it takes a ton of energy, and the whole process is just slow and difficult.
So what do enzymes do? They don't just give the boulder a bigger push. No, that's the hard way. Instead, they do something genius. They build a tunnel through the mountain. They create a completely new, much easier pathway that has a way lower energy requirement. It makes the whole trip fantastically faster and easier. You know, for a while, scientists pictured this process like a rigid lock and key. With the molecule, we call it the substrate, fits perfectly. But we now know it's much more dynamic than that. It's actually more like a firm handshake. That's called the induced fit model. And it shows that the enzyme actually changes its shape a little bit to get that perfect grip, creating the ideal little pocket for the reaction to happen.
Okay, this is a fantastic analogy for what's happening. Imagine trying to get a sweater onto a flailing, uncooperative baby. It's a struggle, right? That super awkward arms everywhere position is what chemists call the transition state. An enzyme acts like a parent, gently grabbing the baby's arms and guiding them into the sweater. It stabilizes that difficult, awkward state to make the whole process just effortless. Now, enzymes don't just have one speed. They're not just on or off. Their activity is fine-tuned, constantly adjusted. It's like a car. You've got an accelerator, you've got brakes. So let's take a look at the dials that control an enzyme's speed.
First up is just the amount of work to do. We call this the substrate concentration. The more substrate you give an enzyme, the faster it works. Makes sense, right? But eventually, it gets completely saturated. It hits a maximum speed called Vmax. At that point, it is literally working as fast as it possibly can.
Temperature is another huge one. For our human enzymes, activity is at its peak right around our normal body temperature, 37 degrees Celsius. A little bit warmer can speed things up, but if you get too hot, the enzyme starts to lose its specific shape and just stops working. We call that denaturing. And that's exactly why a very high fever can be so dangerous.
And just like temperature, every single enzyme has a favorite pH level. The enzyme pepsin, for example, is what digests protein in your superacidic stomach. It loves a pH of about 2. But then an enzyme called trypsin, which works just a little further down in your intestine, needs a much more neutral environment to do its job. This specialization is absolutely key to how our bodies work.
Okay, but sometimes you need to hit the brakes.
That's where inhibitors come in. There are a couple of types. You've got competitive inhibitors. These are basically imposters that look a lot like the real substrate, and they sneak in and steal its parking spot right in the active site. Then there are non-competitive inhibitors. They're a bit sneakier. They bind to a totally different spot on the enzyme, which causes the whole thing to change shape so it can't work anymore. It's like letting the air out of the car's tires. The car's still in the spot, it just can't go anywhere.
And listen, this isn't just some abstract textbook concept. This is how some of our most powerful medicines work. Statin drugs are a perfect example. They are competitive inhibitors that are designed to perfectly block the active site of a key enzyme we need to make cholesterol. And by doing that, they effectively lower cholesterol levels for millions and millions of people. All right, let's zoom out a bit, because understanding enzymes isn't just for biochemists in a lab coat. They are incredibly important tools in medicine, diagnostics, and yeah, even in your laundry room.
This is where things get really cool. Enzymes can act like little diagnostic spies for doctors. When cells in your body get damaged, say in your liver or your heart, they leak their contents into your bloodstream, and that includes their specific enzymes. So by measuring the levels of enzymes like ALT or creatine kinase in your blood, doctors can pinpoint organ damage and diagnose things like liver disease or even a heart attack.
And the applications are just everywhere. We already talked about statins, but guess what? Aspirin and penicillin are also enzyme inhibitors. The bioenzymes in your laundry detergent, they're busy breaking down tough protein and fat stains, and they are absolutely essential for making foods we love, like cheese and yogurt. They really are nature's tiny workhorses.
So, when you really get down to it, from powering every single beat of your heart to helping clean your clothes, enzymes are the microscopic sparks that animate our entire world. They work with a speed and a precision that we can still only dream of. So the final thought I want to leave you with is this. Now that we're starting to understand their secrets, now that we could even engineer them ourselves, what problems will we solve next?